So today we're going to talk about the calculus of inverse trigonometric functions. So if we have like y equals the inverse sine of x, to go through our formula that f prime of x is the limit as h approaches 0 of the inverse sine of x plus h minus the inverse sine of x all over h, that would be a correct statement to make, but you can't do any algebra past that to actually solve what that limit is. So we're going to do something that we kind of did a little bit earlier when I was showing you how to take derivatives of inverse functions. Since this is an inverse function, maybe we can use the same idea and take the sine of both sides. The reason we would do that, because the sine of the inverse sine, because they're inverse functions, undo each other, they cancel each other out, and you're back to x. So since we want to find the derivative of this function with respect to x, we're looking for dy dx, we're now going to take the derivative implicitly with respect to x. Well, the derivative of the sine of y with respect to x is the cosine of y times y prime, and the derivative of x with respect to x is 1. And what we're trying to find is this y prime. So y prime is going to be 1 over the cosine of y, which just happens to be the secant of y. So we've got an answer, but the bad part is that it's in terms of y. We'd like to have it in terms of x. Well, we can do that because we know what y is in terms of x. So we can say it's the secant of the angle whose sine is x. And again, that would be correct, but it's kind of complicated. So maybe we can even do better. What is the angle whose sine is x? Well, if I just were to make that angle like that and say, oh, that's the angle whose sine is x. Right now you wouldn't believe me. But if I did this, now you would believe me that it's the angle whose sine is x, because the opposite over the hypotenuse is x. By Pythagorean theorem, this side would be the square root of 1 minus x squared. So we don't actually have to find out what that angle is. We just need the secant of that angle. Well, the secant is the hypotenuse divided by the adjacent. So you get 1 over the square root of 1 minus x squared. I think that's nicer than that. They're both correct, but this is something that would be more easily to use. So I'm just going to put that as our new formula. Now let's see if we can do the same thing with the tangent. Let's take the tangent of both sides. And the tangent of the inverse tangent of x is just x. And now I'll take the derivative of both sides with respect to x. The derivative of the tangent is the secant squared of y, and since that y isn't x, I multiply by its derivative, and the derivative of x with respect to x is 1, so I get y prime is 1 over the secant squared of y, which is the cosine squared of y. So there again is an answer, but it's got a y in it. So we're going to make it the cosine of y, which is the angle whose tangent is x, and then we're going to square that. And I'm going to use a similar thing that I did up here. What does the angle look like whose tangent is x? If I just did this, you wouldn't believe me. But if I did that, now that is the angle whose tangent is x. And I don't need to find that angle. I just need to find the cosine of that angle. Well, the cosine is going to require the hypotenuse. So I go back to Pythagorean's theorem, and I've got it. So now the cosine is this divided by this. But then I have to square it. So then I would have a formula. 1 over 1 plus x squared. And that's kind of a nice formula. So I'd say so far, this is all derivation. These are the new formulas that we've learned. So we could do this problem right now. It's the inverse sine of, well, it's not x, it's 2x, so we're going to have to do the chain rule, which means dy dx is 1 over the square root of 1 minus x squared. But since that's not x, we do two things. We put in the function, and then we multiply by the derivative of that function. That's what the chain rule has been telling us all the way along. So the final answer would be 2 over the square root of 1 minus 4x squared. Okay, another derivative. Now this time, just to show you, there's two different ways you can write the inverse tangent of x. The way like this, or you can say it's the arctangent. So if you don't like this, you're always allowed to just make this so to take the derivative f prime of x, I've got to use this formula, and again I have to use the chain rule. So I go 1 over x, 1 plus this function squared, but then times the derivative of that function, which is 6x. So I get f prime of x is 6x over 1 plus 9x to the 4th. But I want to find f prime of negative 1, so it would be negative 6 over 10, or negative 3/5. So there's a couple of derivatives. Now, even though these functions do show up once in a while in the real world, they're not as common as most other functions. But what's really going to be important is not the derivatives of these functions, but we're going to come up with a new antiderivative formula. If the derivative of the inverse sine of x is this, then the antiderivative has got to be the inverse sine of x plus c. And the same thing down here. But since these are going to become new special forms, we don't want to be able to do just this one integral. We want to do all the different forms. We're going to rewrite this with u. So we have du over the square root of 1 minus u squared is the inverse sine of u plus c. And we have the integral du over 1 plus u squared is the inverse tangent of u plus c. These are the most important thing that we've learned today, because this is not, these two forms are not unusual that you might get an integral that looks like them. So just to kind of go back to where we are in this course, how many forms do we have? Because these are the last two that you need to know for this year. We started out with 6 trigonometric antiderivatives. The sine, the cosine, the secant squared of u was the tangent of u. So you've got all those, that's 6. Then we did, the first one we did actually was u to the nth du. which was u to the n plus 1 over n plus 1. And then we did du over u, which was the natural log. And then we did e to the u du, which turned out so nicely. And then we did a to the u du, which was almost as nice, but we got that extra constant in there. So we have 6 trigonometric plus 4 is 10. Now these two, so we have 12 total forms that when we get an integral, we have to look at, I wonder which one this is. So let's try one example right here. This one of the 12 forms, I'm hoping you see, looks a little bit like this one right here. I see 1 plus u squared when I look at that. So if that's true, I want u to be the sine of x, because then I can call all of this 1 plus u squared. The 5, oops, I forgot my dx right here. Always have to have a dx in your integral. So I've got left the cosine of x dx. Well, that's exactly what du turned out to be. So I can call all of that du, and I've got it exactly in this form. So the answer is just going to be 5 times the inverse tangent of u plus c. But I never want to leave my answer in u when the problem was in terms of x. So I just put that back in as the sine of x, and I've got an answer. So that's our first integral that we've taken using one of these new forms. So let's just do a couple more examples over on this other board. We have another integral, but this one, it's a definite integral. So we're going to get a number as our answer. This one is a little bit more difficult to figure out which form it's in. But I'm going to show you what I would pick and see if you can understand why I picked that. I'm going to pick u to be the square root of x. Because then I can call this 1 plus u squared. Now I still have this other stuff to deal with, but let's see if it works out. Du could be, this is x to the 1/2, so du is 1/2 x to the negative 1/2, or 1 over 2 root x dx. That's almost what I've got. That's what I have left to deal with. So I think that's going to work out nicely, because I can call this right here 1 plus u squared, and then dx over the square root of x right here is just 2 du. Now, these numbers here, these limits on our integration are going to be x values. We want to get them in terms of u. So the square root of 1 is 1, and then, actually, sorry, let's make that 3. And this is going to be the square root of 3. It would work the other way, but I had really meant that to be 3, so it works out a little bit easier in our final answer. So then, what is the antiderivative of this? It's the inverse tangent of u. So we get 2 times the inverse tangent of the square root of 3 minus the inverse tangent of 1. Now, this is why we have to review a little bit of our inverse trigonometric functions. If I make an angle, that's the angle whose tangent is the square root of 3, it would have to look like that, which means this side would be 2. So the 30-degree angle is up here by geometry, so this is 60 degrees. So that's pi over 3. And then if we do the same thing and make the angle whose tangent is 1, it would have to look like this. 1 over 1 is 1. And we know right away that that's got to be a 45-degree angle, or pi over 4. So altogether we get pi over 12 times 2, or that answer. That's a number that would be the answer to this definite integral. So that one was a little bit tougher. Okay, find the area. So now I'm going to start, we're getting so close to the end of the year that I've been trying to review some of the ideas that we've learned during the year. So find the area between the graph of y equals x and y equals 2 over 1 plus x squared from 1 to the square root of 3. So 1 and say the square root of 3. So if I put in 1 here, I get 1. If I put in the square root of 3, I get a half. So that function's coming down like that. And y equals x, we know is going to go like this. So the area we're looking for is right in here. And I think you can see the best way to make your rectangle is up and down. I don't want to resolve these. Well, this one wouldn't be hard, but that would be a hard one to resolve for x. So now I'm ready to take my area. It's the integral from 1 to the square root of 3. And what is the height of this rectangle? It's the y value on this straight line minus the y value on this curve. And the width of the rectangle is dx. So if I can solve that definite integral, I'm going to get the area. Now you can do it all together, but especially when you're first beginning, I would split these up. Make that integral minus that integral. And you can bring the 2 out front if you'd like. So this one is just x squared over 2 from 1 to the square root of 3. And this one is exactly in the form of the inverse tangent. We don't have to do any kind of use substitution in this one. So altogether, what do we get when we plug things in to this side? 3 halves minus 1 half is 1. And then we have the inverse tangent of the square root of 3. Oh, we just did these up here. That makes it very nice. The angle whose tangent is square root of 3 was pi over 3. And the angle whose tangent is 1 is pi over 4. So we get 2 times pi over 12, or we get that pi over 6 again. Just happened to show up similar to that last problem. So that's a little bit of review of area problems. Well, what's another important thing we've done this year? Find the max and min. When they say that, when they don't say local or relative, they mean max, absolute max and absolute min. So how do we find them? We know they're either going to be at critical values or at endpoints. And we've got 2 endpoints. Our domain is from 0 to 6 for x. So the first thing you're going to do is take the derivative, because that's going to give us our critical values. Well, this is the inverse tangent. This new derivative is 1 over 1 plus x squared. But again, we don't have x, we've got a function of x, so we do the chain rule. So it's 1 over 1 plus that function squared. Then times the derivative of that function. And what am I going to do? Look for critical values, so I set it equal to 0 or undefined. Well, the only way you get a fraction equal to 0 is if the numerator equals 0. So that's going to be at x equals 2. And you could get an undefined derivative if the denominator was equal to 0. But since this is squared, there's no way you're going to get the denominator to 0. So the only critical value is at 2. So our domain is from 0 to 6. That's our only critical value. And I can see, since the denominator is always positive, that the whole derivative is going to be negative until you get to 2, and then it becomes positive. So the function f starts out at something, goes down until it gets to 2, and then it goes back up because the derivative is positive. So right away I can say my absolute minimum is f of 2. And what is f of 2? It's the inverse tangent of 4 minus 8. I can say that that's the absolute min. Now the absolute maximum is either going to be at this endpoint or this endpoint. So we have to plug them both in. And we get 0 when we plug in 0. And what's the angle whose tangent is 0? That's going to be 0. Then we put the inverse tangent, and when we plug in 6, we get 36 minus 24, or 12. So we want an angle whose tangent is a positive number. So we now know from our knowledge of pre-calc that that's got to be a positive number. So it's bigger than 0. We don't know exactly what that number is, but it's bigger than 0, what that angle would be. So this has got to be our absolute max. And this is a negative number because the angle whose tangent is a negative number is going to be in the fourth quadrant. It's going to be a negative angle. So there's a max-min problem. So let's end up with a related rate problems. We have a 10-meter ladder slipping away from a wall. So draw your wall, your floor, and your ladder. I guess the ladder doesn't go through the wall. So what do we know about this? As that ladder slips, this distance between the wall and the bottom of the ladder is changing. So we call it a variable. The distance between the floor and the top of the ladder is changing. We're assuming that the ladder is not changing. It's still 10 the whole time. What do we know? We know how fast the ladder is slipping away from the wall at a rate of 2 meters per second. So that's the rate at which x is changing. And it's getting bigger, so dx dt equals 2. And what are we trying to find? The rate at which the angle between the wall and the ladder. So that's going to be this angle. We want to know how fast it's changing. So I call that a variable. Why not theta? Now I'm going to need a relationship. I don't know anything about y. I do know the rate at which x is changing. And 10 is a constant. So it makes sense to use the opposite and the hypotenuse. So I'm going to just say theta equals, that angle is the angle whose sine is the opposite over the hypotenuse. And now I can just explicitly solve for what I'm looking for. d theta dt, the rate at which theta is changing with respect to time. And our new formula is 1 over 1, the square root of 1 minus x squared. But it's not x, it's x over 10. So I have to put x over 10 and then multiply by the derivative of x over 10. But be careful, it's with respect to time. So it's going to be 1/10 times dx dt. The derivative of x with respect to x is 1, but the derivative of x with respect to t is dx dt. So I want to find d theta dt at what time? It says when the ladder is 8 meters above the ground. So that's when y is 8, but we don't need y, we need x. So x is going to be 6. This is a 3, 4, 5 triangle. So I'm going to say when x equals 6, and I get 1/10, dx dt we know to be 2 over the square root of 1 minus 6/10 or 3/5 squared. So 9/25. So we get 1/5 in the numerator, and we get the square root of 16/25 or 4/5 in the denominator. So altogether, we get 1/4. And it's d theta dt, so it's going to be in radians per second. And it's positive, so that means that angle's getting bigger, which kind of makes sense as that ladder's slipping, that angle is going to be getting bigger. Now, just before we stop, I just want to make sure you know, we could have done this problem without knowing this about inverse sine functions. We could have just said the sine of theta is x over 10 and solved it, take the derivative with respect to t and solve it implicitly. But this just gives you another perspective on how you can use inverse trigonometric functions. And I think we've reviewed 3 important concepts along with what else we were doing in this video. So, take care.